lecture, we're going to discuss about singular perturbation. I've given a hint in the last class as to what the premise of singular perturbation is, and we'll start with that premise where the highest order derivative will be multiplied by a small number. So let us consider the following differential equation. Now, this is a second order differential equation, and let us define the two boundary conditions. Alright, so we have a domain spans from 0 to 1, and y at 0 is 0 and y at 1 is 1. And there is some functional behavior, something like this. We don't know what it is. But yeah, we'd like to find out what it is. So before going into the approximate solution, it is worthwhile looking into the analytical solution for this. And obviously the analytical solution does exist. So let y be of the form e to the power mx. So what do we have over here? We have epsilon m square plus 2m minus 1, this whole thing times e to the power mx equal to 0. And you will obtain this once you substitute this equation over here. And now if this is equal to 0, then epsilon m square plus 2m minus 1 equal to 0, which implies that m equal to minus 2 plus minus under root 4 plus 4 epsilon by 2 epsilon, right? These are the roots, which imply that m1 will be minus 1 plus square root of 1 plus epsilon divided by epsilon, and m2 will be 1, rather minus 1 minus 1 plus epsilon by epsilon. So fine. So now we can write down the solution for y as a to the power m1x plus b to the power m2x. Let us use the first boundary condition, 0 equal to a plus b. Fair enough. And the second boundary condition will yield 1 equal to a to the power m1 plus b to the power m2, because x equal to 1. So now because b is equal to minus a, so this becomes a e to the power m1 minus e to the power m2, and this implies that a is 1 over e to the power m1 minus e to the power m2, while b is equal to minus a. So now with the help of this we can go ahead and make a plot of this function. So let me just grab the starting code. Let me define x. Then let me define epsilon 0.1. What else do we need? So we need to define m1, we need to define m2, we need to define a, and we need to define b. So m1 is minus 1 plus, what is it, 1 plus epsilon, this whole thing divided by epsilon. Well, this bracket term is raised to the power 0.5. Alright, so let me, oops, this should be a bracket, yeah. So let me copy this, m2 is equal to this, but the sign over here is negative. A is 1 over m1 minus minus m, rather m2, and b is simply minus of a, right? So then y is, or let me put it, y exact is what? It's gonna be a times np dot exponential of x m1 times x plus b times np dot exponential of m2 times x. So then let's plot it. Okay, so we have this kind of behavior, and we see that. So what do we observe over here? There's a zone near x equal to 0, not near x equal to 0, but it's towards the x equal to 0 boundary, where there's a fast variation in the solution, after which it gradually goes. And let us change the value of epsilon to see whether, I mean, what the effect is. So when we make it 0.1, the variation appears to be sharper. In fact, we need to have a finer resolution for x in order to view that rapid change. So let me take 200 points. So yeah, so you have a fast variation over here, and then a smooth variation, something like this. And this kind of thing is called as a boundary layer. So a boundary layer refers to that zone in the domain where there is a very rapid change in the variable. And the term boundary layer is very closely associated, or in fact, von Karman is sort of credited for assigning this name. So very near a wing of an aeroplane, what happens? So there's fluid, or rather air, which is relatively flowing with a very high velocity because the plane is flying at a very large velocity. So very near the wall, the effects of viscosity cause the very first layer of fluid to slow down. So the fluid which is away from, or rather air which is away from the wing, it doesn't really feel the effect of this velocity, but air very close to the wall will feel the effect. So there will be some region near the wall which feels the effect of the velocity, but the outer region does not feel the effect of the wing. So this is the outer region, whereas the region in which effect of viscosity is felt, the effect of viscosity is manifested as a no slip boundary condition at the plate, and so this region is the inner region. And typically this the thickness of the region over which the change happens is maybe 5 millimeter. It's quite small compared to the scale of the wing. For example, the wing could be several meters wide, so it's quite thin. So if we now plot the velocity profile at some location, we will have a rapid change in velocity, and then it will remain more or less constant, right? And this region near the wall is termed as the boundary layer. And such boundary layers exist for Reynolds number quite large. So Reynolds number, for those of you who are from a fluid mechanics background, a high Reynolds number indicates that the flow is dominated by inertia rather than viscosity. But despite that dominance, right? So those of you who are from a fluid mechanics background, they will realize that viscosity manifests itself in the momentum equation through a term which looks something like this. And when the flow is dominated by inertia, this particular effect is quite small. Effect of viscosity is quite small. But if we neglect this term completely, The equation, the momentum equation, instead of being a second order equation, boils down to a first order equation. And a first order equation won't be able to satisfy two boundary conditions simultaneously unless the two boundary conditions are consistent. That's a trivial case. Near the wall, the velocity is zero, but far away from the wall, the velocity is equal to the free stream velocity. It has to satisfy these two boundary conditions. If viscosity is not there, then u equal to 0 is no longer the boundary condition which the flow would satisfy. We cannot enforce no slip in the absence of viscosity. And it is this viscosity in such inertia dominated flows that allow for a small region near the wall of the wing or plate or whatever it may be to sort of have that viscous effect beyond which the effect of viscosity does not dominate anymore. For those of you who are from a chemical engineering background, consider a catalyst pellet. So this catalyst pellet, suppose there is a fluid over here, right? There is some fluid and the catalyst reacts with the fluid. So imagine I draw a transect like this, and when the catalyst has not yet begun reacting, I can plot the concentration as something like this. It is zero inside the catalyst, and suddenly it has some concentration in the bulk, and this is the bulk concentration. Now the catalyst starts reacting with the fluid. Maybe it makes some product. We don't care about that. So there will be depletion of concentration near the surface of the catalyst. So it will be still zero, and then it will be something like this. This there is a sharp gradient going from the catalyst to the fluid, and a sharp gradient leads to diffusion. Gradient leads to diffusive flux. But if the diffusivity is quite small, this profile that I'm drawing, it will be slowly propagated towards the bulk. If the diffusivity is quite small and the reactivity of the pellet is quite high, the profile would look something like this. It will be depleted, the fluid concentration will be depleted, or rather the reactant concentration will be depleted near the catalyst pellet, but fluid has not yet, or rather the concentration from the bulk has not yet been able to replenish that lost reactant near the surface of the pellet. If the diffusivity were to be high, then the reactant would rush in from the bulk towards the pellet, something like this, and we would have mild gradients in concentration. So this case where the reactivity is high but the diffusivity is low, right? Even that leads to the formation of a concentration boundary layer near the surface of the pellet. So with these two applications in mind, let us now look at how we can analytically solve at least this synthetic problem. You can of course apply these techniques to various problems that you might encounter, but the point that I'm trying to make is they will have the same hallmark, that is, there will be some parameter which will be multiplying a higher order term, and dropping that term would lead to reduction in the dimensionality of the problem if I want to cast it in that particular form. So let us do the naive perturbation that we did in the case of regular perturbation. Let me consider y naught plus epsilon y1 plus so on, in the hope that this particular sequence converges. Let me substitute this over here. So what do we have? Epsilon y naught double prime plus epsilon square y1 double prime plus so on. second term will be plus twice y naught prime plus twice epsilon y1 prime plus twice epsilon square, we don't care about the epsilon square terms, minus y naught minus epsilon y1 and so on. So I'm just writing the maximum order as epsilon square, but we don't want to go so far, so we can drop this as well. So I'm just writing order 1 and order epsilon terms. So now if we isolate the various terms of order epsilon, so at order 1 we would have 2 y naught prime minus y naught equal to 0. At order epsilon we would have y naught double prime plus twice y1 prime minus y1 equal to 0. And now what are the boundary conditions? At y equal to 0, y naught 0 plus epsilon y1 0 equal to 0, which implies y naught 0 is 0, y1 0 is 0. Fine. What about the second boundary condition? So y naught at 1 plus epsilon y1 at 1 equal to 1, which implies y naught at 1 equal to 1, y1 at 1 is equal to 0. But look, at the leading order, we have a first order differential equation, but we are presented with two boundary conditions. Not this, but the two boundary conditions are this and this. So at the leading order, we have 2 y naught prime minus y naught equal to 0, y naught 1 equal to 1 and y naught 0 equal to 0. We cannot satisfy two boundary conditions simultaneously for a first order differential equation. So we must take a call. There must be only one boundary condition which this can satisfy. And we already know from the graph that we plotted that at y1 we must have this being satisfied, right? So so let us write down the solution. Y naught is equal to exponential of, or rather a times exponential of x upon 2, right? This is the solution for this equation. So now let us choose that at y naught 1 we have 1. So using this boundary condition, we have 1 equal to a to the power half, and thus we have 0 y0 exponential of x minus 1 upon 2. So that is the solution. Let us now write down the first order equation, which is y naught double prime plus 2 y1 prime minus y1 equal to 0. We already have a solution for y naught, and so a second derivative of this will be 1 by 4 times exponential of x minus 1 by 2 plus 2y1 prime minus y1 equal to 0. So this equation can be integrated with the help of an integrating factor. Alright, but I'm gonna write down the solution directly. You can try to find it out. So the solution for y1 turns out to be half 1 minus x times e to the power half x minus 1. So this is the solution for y1. So let us do it. Let us construct the outer solution. I'm calling it outer, but from what we've discussed so far, we can write the solution as y1 plus epsilon times, y0 plus epsilon times y1. Let us do it. So let me write down y0 or yo equal to yo0 plus y epsilon times yo1. yo0 is exponential of x minus 1 by 2, and yo1 is equal to half times 1 minus x times exponential of x minus 1 by 2. Then we simply plot. Let's give it a label. I'll call it outer solution. In fact, let me make it as a dashed line style. So let me run this and see what happens. Oh, excellent. So let me reduce this parameter a bit. Rather, let me increase the parameter a bit. Okay, so it is clear that the approximate solution that we've obtained, which we are calling as the outer solution, it does match quite well with the behavior of the equation in the non-boundary layer part, and hence it is called as the outer solution. Much like the region away from the wing, it is the outer region, right? Oh, sorry. So it satisfies, and as epsilon becomes smaller, the approximation becomes better. But what is the caveat? Obviously, the outer solution has been found out using only one boundary condition, that is the boundary condition at x equal to 1. We have nowhere utilized the other boundary condition, that is at x equal to 0. And in fact, at each hierarchy, right, so this is the first equation, the second equation, at each hierarchy, this is the equation for actually y1. It is not an equation for y0, because y0 has been already obtained using the leading order equation. So each hierarchy, each equation appearing in the hierarchy will be first order. So you will never be able to satisfy the boundary condition at x equal to 0. But there must be a way. There is obviously some functional form which is different than the outer solution that is happening inside the inner region. So how do we find that out? Okay, that is the question. Well, so far we have not done anything which is different from the regular perturbation business. So now we will do rescaling the coordinate. So we must now rescale the coordinate so that we can have some region in which this particular term will be important. Let us see how we can do that. So we have the equation over here. So let us consider small x as epsilon raised to some alpha times some capital X. So essentially what we're doing here is we're rescaling the coordinate. So depending on the smallness of epsilon, we must then appropriately choose x to be quite large, rather capital X to be quite large. I mean, that should come out naturally as a consequence of the analysis that I'm going to show. After substituting this, let us see what happens. So let us denote the solution of y in the rescaled coordinate system as capital Y. So what do we have? Epsilon d to capital Y, now dx2, but this will be epsilon raised to 2 alpha dx2 plus twice d capital Y d capital X epsilon raised to alpha minus capital Y equal to 0. Let us now analyze the different orders of magnitude of the three terms. So the first term has an order of magnitude 1 minus 2 alpha. Second term has an order of magnitude as epsilon raised to minus alpha. Third term has a term which is order 1. Now, how do we know that these are the orders? It is because we are going to assume that upon rescaling, the dy dx or d2y dx2, they will behave more uniformly over the domain, over the compressed domain. That is, they will now be assumed to be order 1, and thus the order of that particular term will be decided purely by the prefactor, that is, these terms. Let us now assume. See, we know for a fact that the second derivative has to exist in order for us to somehow satisfy the condition at the left boundary. So this term definitely has to exist. But now, in order for that to exist, it must coexist with one of these two terms. So suppose this exists with this term. So what do we have? 1 minus 2 alpha equal to minus alpha. That yields alpha equal to 1. So this is balance of 1 and 2 terms. The balance of 1 and 3 yields 1 minus 2 alpha equal to 1, which implies alpha equal to half. So now if we go by alpha equal to 1, then what do we have? The orders of magnitude will be epsilon raised to minus 1, epsilon raised to minus 1 and 1. So even in this case, what is going on? These two terms of the same order of magnitude, but they are smaller than the order of magnitude of the third term, which is simply 1. So this is clearly not allowed because we are essentially then dropping another order of the equation. Come on, we can't have that. We need to somehow keep the second order derivative as the dominant term. What about this? When alpha is half, this order of magnitude becomes epsilon to the power 0. This order of magnitude becomes epsilon raised to minus half, and this becomes epsilon raised to 0. So now these are the highest order terms, while this term is smaller. So we have the last term as order 1, while if alpha is equal to half, what are the different terms? This particular term will be order 1, this particular term will be epsilon raised to minus half, this particular term will be order 1. So over here, what do we have? Epsilon to the power minus 1. So when epsilon will be small, this is 1 by epsilon, so this term and this term will dominate. So essentially, the higher order term is the second order term is being retained over here. But when we have this is the largest order term because this is 1 by epsilon raised to half. And epsilon when it's small, it's going to be much larger than 1. So here we're actually again losing out on that higher order derivative. So this has to be the correct scaling. So alpha equal to 1 is the correct scaling. Alright. So if alpha equal to 1 is the correct scaling, then what do we have? In that case, the governing equation will look something like this. Plus dy dx is equal to 0. And so this equation can also be solved by assuming that capital Y is of the form e to the power m capital X, right? And this gives us m square plus m equal to 0, which implies m equal to 0 and m equal to minus 1. Therefore, the solution will be y equal to a plus b e to the power minus capital X. I think I'm missing a factor of 2. Yeah, there's a factor of 2 over here which I missed. So there will be 2, and so this will be minus 2, and this will be minus 2x. Right. So now we must find out the two boundary conditions that this will satisfy. Okay. Now this is a second order differential equation. Now, this has to satisfy two boundary conditions. So obviously the first boundary condition will be capital Y at 0 will be 0. And this is the left boundary which we have not utilized in finding out the outer solution. But what about the inner solution? Rather, what about the other boundary condition? Now obviously we have done something to make this second order derivative exist in this equation, and that thing is finding out a rescaled coordinate so that the second order derivative is now relevant in the problem, unlike the first approximation where it completely went to 0. So alpha was equal to 1. So let us see what happens to the coordinate in that case. So when alpha equal to 1, this rescaled coordinate becomes capital X equal to small x upon epsilon. It means that for small values of x also, and I will obtain a large value of capital X because epsilon is small. And so that implies that, let us look at this variation. I mean, I can explain it using this variation. So we have a fast change and then smooth change. So we are taking this domain where there's a fast variation and we are magnifying it so that the zero boundary still remains 0. But suppose this change happens at 0.05. Okay, this change is happening at x equal to 0.05. But I'm dividing it by epsilon, meaning I'm magnifying that 0.05 to something very large. Epsilon in this case was 0.01. So 0.01 and this becomes 5. Essentially, this boundary becomes magnified, it becomes large. So the other boundary conditions comes from the principle of matching. That is, capital Y for large capital X, large values of capital X meaning x tends to infinity, should match with small y for x tends to 0. That is, this is from the outer solution. So x tends to 0 for the outer solution means for the dashed line over here, whatever limit it is going, so this dashed line is sort of going to this. So this boundary is like x tends to 0 for the outer solution. And why is it true? Because obviously it cannot satisfy the x equal to 0 boundary condition. So as x tends to 0, this obviously does not satisfy the left boundary condition. And hence we must merge these two solutions. One solution from the inside layer, one solution from the outside layer. And we must see how we can match them. Well, we're not going to match them completely, but I'm going to show you the approximate form of the solution in the inner layer. So the solution was this. So what is the limit as x tends to 0? Capital Y as x tends to 0, small x tends to 0 is exponential of minus half. Alright, so capital Y, so this is the solution, and the first boundary condition is this. So y is 0 equal to 0, so obviously a will be 0 because once we substitute x equal to 0, this, sorry, the a plus b will be equal to 0, not equal to 0. Okay, so first boundary condition 0 is equal to a plus b. Second boundary condition exponential of minus half equal to a. So now x tends to infinity will make this to 0 is equal to a. So a is exponential of minus half, b is exponential of minus of exponential of minus half. Okay, because when x tends to infinity, this term will go to 0. All right. So capital Y becomes exponential of minus half times 1 minus exponential of minus 2 capital X. Now let us write this expression in terms of the original coordinate system. So this is exponential of minus half, 1 minus exponential of minus 2 small x by epsilon, because this is how we found out the scaling. Let me now plot this particular function and see what happens. So I'm going to call it yi. So it's exponential of minus half times 1 minus exponential of minus 2 times x by epsilon. Plt dot plot x comma yi. Let me make a red dashed line, label inner solution. So yeah, let's plot them and see. Okay, so the inner solution obviously matches quite well in the inner zone, that is for the scaled zone. Outside it doesn't match. But look, the outer limit, that is this flat limit, it matches with the inner limit of the outer solution. So the leftmost limit of the black dashed line matches well with the rightmost limit of the red dashed line. Okay. And that's what we imply by matching. And in fact, let me reduce epsilon a bit. That should make it a bit more obvious. Great. So inside this red dashed line matches, outside this black dashed line matches, and this is how we can. So this is by no means a complete discussion of a singular perturbation method, but I at least hope this gives you an idea of how to go about things. You have two distinct behaviors, one inside the boundary layer, one outside the boundary layer. And you can find out approximations to those functions. In fact, you can find a composite expansion which can give you one single function which will go across both the domains. But that's beyond the scope. But yeah, so let me just show you how we can use some of our old code to solve that equation with the help of SciPy. So we're gonna import solve BVP, and so function we have to. So one moment, what was it? So y prime. So let me call all this as y0 because I want to cast it in the Python form. So let y0 prime be y1 and then epsilon y1 prime plus 2 y1 minus y0 is equal to 0. So I must divide everything by epsilon. So now I will change the return value of the function. So y1 will stay. This will be minus 2 y1 upon epsilon minus y0, rather plus y0 by epsilon. Essentially what I'm doing is I've taken both these terms on this side of the equality, so this becomes equal to minus this plus this. That's all I've modified over here. And the boundary condition at the left boundary it is 0 and at the right boundary it is 1. So nothing changes over here. And xi is the initial guess. It's going from 0 to 1, only 10 points. Guess value, residue. Then for plotting, I'm defining a space xplot. Let me take 100 points. Let me make it dash dot. Yeah, so let me run this and see what happens. There appears to be some error. Let's see what happens. I mean, maybe if we have written something incorrectly. Ah, this has to be 0 point. So we were using 0.1. Okay, so let me run this again. Okay, there you go. It matches so well that it's it's on the blue line. So in fact, let me put the analytical solution with less number of points. Let me just take 6 points and let me mark them with some kind of marker, red marker, square red marker. Let me rerun this. Oh, okay, so it's affecting the other codes as well because I'm deriving all the solutions with the help of this x. So let me make this as 1000. Let me make another copy. Let me call it xe, and let me plot the exact solution with only 6 points. This has to change as well. It's just small tidbits, but yeah, it makes things look much neater. Okay, there you go. Let me put down a label for this as well. We must call the legend at the end so that it's updated properly. Well, there you have it. So with this, I'm gonna close this particular lecture. um, I hope I've given you a very small introduction on regular perturbation, singular perturbation. For more reading, you can look at some of the reference books below or some of the links below. And with this, I'll end this lecture and I'll see you next time with something new. Bye.